everybody, welcome back. We're going to walk through the very basics of the Logit and Probit models with examples in Stata. So let's get right to it. Okay, so first off, the very basics. When would a Logit or a Probit model be appropriate? Well, it all depends on the nature of the dependent variable, right? So if you have a dependent variable, a y variable, that is a binary dummy variable, it only takes on the values 0 or 1, indicating the presence of a particular condition or the absence of that condition. This would be the model for us. So for the example that we're going to walk through today in Stata, we're going to be using a data set from the Studenmund introductory textbook, which is an excellent textbook. The Amazon link for it will be in the description if you want to get your hands on it. And this is from chapter 13 of that textbook. And we have a little pretend data set here with 30 observations. And the variable of interest here is denoted D because it's a dummy variable. And in this example, it's representing labor force participation, right? So it either takes on a value of 0 if the individual is not participating in the labor force, not either employed or actively seeking employment, and takes on the value of 1 if they are employed. So the first question that always comes up is, can't we just do this with ordinary least squares, with a linear model? And technically we can, right? That's what we would call the linear probability model, just running OLS, even though your dependent variable is a 0-1 binary. So in this example, let's say we try to predict labor force participation, D, with the individual's age and years of schooling. So the variables A and S in this example. And the good news is, running this with OLS, we get these coefficients here that are immediately interpreted as marginal effects, right? So for each additional year of schooling, the probability of labor force participation goes up by about 0.10, about 10%. And OLS does provide consistent, unbiased estimates of those marginal probability effects. So now the question is, well, why would we ever not use ordinary least squares, right? And the main concern is that there are no limitations on the predictions from this model. The predicted dependent variables don't have to conform to a probability interpretation. In other words, there's nothing forcing those y hat predictions to be between 0 and 1, which is what we would like to see if it's a probability, right? So following estimation here, if we just go predict, call it D hat underscore LPM, so that's our linear probability model prediction. And then if we bring up the descriptive statistics for this fitted value, so summarize or sum D hat underscore LPM, in this particular case, we see that we have values with a minimum of 0.06, which is reasonable, but a maximum above 1. So we're predicting some individuals have a greater than 100% probability of this event occurring, in this case, participating in the labor force. So thus enters the Logit and the Probit model. So that's one way to think of the initial kind of motivation, is that we want a nonlinear model that forces the outcome, the prediction of that function, to lie in that 0-1 range. So both the Logit and the Probit are derived from cumulative density functions. For the Logit, it's from the logistic or the log normal distribution. For the Probit, it's the standard normal distribution. And that's where our regression functions, our prediction functions come from. So we'll use kind of this notation here of G of x beta. So x beta is the B0 plus B1x plus B2x2. And the G is the function into which we put that linear combination. So in other words, the linear probability model is just x beta predicting y. Here it's some function, g of x beta. And it's the choice of that g function that differentiates the logit versus the probit. Okay. So what you can show fairly easily is that in both of these cases, the fitted probability, the probability that y is equal to 1 conditional on x, coming out of either of those g functions, will have 0 and 1 as their limits. So as the input goes to infinity, that g function becomes asymptotic at 1. When the input x beta goes to negative infinity, the output becomes asymptotic at 0. So that's all well and good, right? What that means, of course, is that our regression estimation is no longer linear in parameters, right? So how do we come up with the beta hat coefficient estimates? Well, we can't use an ordinary least squares estimation anymore. So in both case, the logit and the probit, we use the maximum likelihood estimator. Now you'll want to consult your textbook, of course, for more details, but the basic idea is that we want to choose the values of those parameters, the b hats, that maximize the joint probability of observing the outcomes that we see. The ones for the ones, the zeros for the zeros, if that makes sense. So the construction of the function looks like this. So it's the product of each observation's probability of observing what we see. So this term here, pi to the power yi, well, the yi is the 0 or the 1, right? And when that takes on the value 1, we get pi to the power 1, but 1 minus pi disappears because 1 minus 1 would be 0. So it's the probability of seeing a 1 when a 1 actually occurs. When it's a 0, pi to the power 0 goes to 1, and we're left with 1 minus pi, the probability of seeing a 0, to the power 1. So each of those terms kind of blinks on and off depending on what the actual outcome is. Now what you'll see when we do the estimation is that we will have a log likelihood value. So we take the natural log of this product across our n observations, and it's going to become this summation. But again, it's the summation within these probabilities. And again, what differentiates the logit and the probit? This function is going to be the same for either, but it's how we model that probability, that g of x beta function. Going back, it's either going to be this little monster, the cumulative distribution for the standard normal, again, that's the area under that bell curve, or it's going to be the exponential function in the logit. So let's take a quick look at the probit estimator here. So in Stata, the command creatively is just probit, and then otherwise it's exactly like the regress command. So we put in the dependent variable, and then the independent variables in this case, again, let's say age and schooling, S. And what we should see is this likelihood estimation. So these are iterations on that log likelihood value. So Stata behind the scenes is plugging in different values for our coefficients until it gets to the optimal value, the maximum joint probability, the maximum likelihood. And then we see our coefficient estimates here, and we'll come back and talk about those in a second. But let's just first kind of see, did we overcome the problem that kind of led us down this road in the first place if we take the predictions from this model? So let's go predict, and again, it's the predicted dummy variable here, d hat, but now let's go underscore PR for probit, and then we can summarize that value, and mathematically, what we have done is created a function that will push those predicted values always to lie between 0 and 1. So the linear model, we saw a maximum value greater than a 100% probability. Here we've avoided that problem. There are other motivations, but that's kind of the easiest way to think about it. So now, what else can we take out of this estimation, right? Well, the first thing we always do with regression is typically look at the coefficients and see if they make sense, if they are what we expect. And our natural inclination is to see these as our usual slope coefficients, the marginal effect of x on y. Well, in this case, because that b, that coefficient, occurs within a nonlinear function, these terms here, these beta hats, are not the marginal effects. Mathematically, what we would have to do, right, is take the derivative of g of x beta with respect to x, which is going to be the coefficient on x, the b1 here, times the derivative of g with respect to x beta. Here's where the Logit model makes life a lot easier. It's a lot easier to see and manipulate what that derivative function is going to look like. You don't really want to have to take the derivative of the integral of the standard normal density. But the good news is Stata does it for us either way. Right, so usually when you're running the Probit model, the first thing you're going to want to do is type in mfx after you estimate. That gives us the marginal effects, which we can now compare to our linear model, and which actually have useful interpretations. So here, we've estimated that each additional year of schooling, holding age constant, adds 0.12 to the probability of labor force participation. Probability goes up by about 12 percentage points. Pretty close to what we had with the linear model, which was about 0.10. Okay, so let's do the same thing with the Logit model and see if we're in the ballpark with those marginal effects. So again, the good news is the command, it's just the name of the estimator here. So Logit, the dependent variable, and then our independent variables. So labor force participation as a function of age and schooling, but with that logistic G predictor function. And again, the coefficients that we estimate here, those are within that G function. They are not the marginal effects. So we follow this up with mfx. And these are the associated slope coefficients. So here, for every 1 unit increase in schooling, we're predicting that 12 percentage point increase in the probability of labor force participation, virtually identical to what we had with the Probit. Now, a few notes here on this mfx command. Remember, when you're taking the derivative of that g function, it's evaluated at specific inputs, right? All the values of the beta hats and the values of our x variables. So the default is to plug in the sample mean for each of those x variables, but we can adjust that here, right? So if we typed in mfx and then we use the option, so we go comma at, and then in parentheses, mean, well, that should replicate exactly what we just did, but we can now adjust it using a variation of that same thing. So we can go mfx, and again, that's going to refer to the most recently estimated set of coefficients. And let's say we want to put it at the mean of all variables, but we want schooling to equal 10. So this would be calculated the marginal effect beginning at 10 years of schooling, and then we can calculate the associated marginal effects here. And so what you'd want to look for is meaningful differences. So let's rerun that Logit model and add in a dummy variable accounting for marital status of the individual. So here, it's going to be our Logit again, dummy dependent variable as a function of age, schooling, and marital status. And let's just jump right into the marginal effects calculation. So we say at the means, except let's do it for unmarried individuals. So m is equal to 0. And then let's do it exactly again, mfx at mean, but now when marital status is equal to 1, essentially what we've done is constructed the equivalent of a slope dummy interaction term, right? So the effect of schooling for unmarried individuals has an effect of 0.05 on the probability of labor force participation, and it's 3 times that for married individuals. So this is an easy way to look for sensitivity of marginal effects to different variables. But it's all coming from that same MFX command. And the other key point is it's not coming directly out of that Logit or Probit function. And this, calculating marginal effects at differential values, that applies equally to the Logit and the Probit. Now, one advantage of the Logit model that sometimes is going to be very useful is, again, that the mathematical formula for that probability prediction is a lot easier to manipulate, and it has some additional interpretations. So sometimes you'll see what we would call a logistic model or an odds ratio interpretation of that Logit probability predictor. And this gets into the weeds a little bit, but the difference between odds and probability is the odds of an event is the ratio of the probability of event occurring relative to the probability of that event not occurring. So in this case, the probability of a 1 divided by the probability of a 0. So sometimes it's easier to think in odds than in probabilities, and with a little bit of mathematical manipulation, we can derive what that odds value is going to be. So if it can be shown, right, that the odds of an event occurring, the probability over 1 minus the probability, right, takes on this value e to the beta x from a Logit prediction model. So we can calculate the odds of the event occurring at x plus 1 relative to x. So basically all we're asking is, how do the odds of the event occurring change as x goes up by 1 unit? Essentially the marginal effect on the odds. And again, with a little mathematical manipulation, go back and look at your textbook, it can be shown to be e to the power beta 1, the exponential of the estimated coefficient. So how do we get that and interpret that in Stata? Well, remember the command that we did to estimate the Logit model was Logit. Here, if we type in logistic as the command, it'll do this for us. We could go back and recover this just taking e to the power beta hat. But if this is what you really want to calculate, you can do it from the beginning. So we would go logistic d as a function of age, schooling, and let's add in marital status again. So we see something like this. The odds ratio for that schooling variable is, let's call it 1.96. So for every 1 unit increase in the years of schooling, the odds of labor force participation doubles, right? It's a 2-to-1 ratio, essentially. When we see these values here less than 1, that tells us that ratio is less than 1. So as x goes up, the odds fall, or the probability falls. Okay, so that's something that you can't do, at least not easily and not directly, from the Probit model. Okay, a couple other things to consider here is our measures of goodness of fit, right? So in OLS, we're used to seeing an adjusted R squared, an R squared, and an F statistic. Because we're not using OLS, when we're using maximum likelihood, we have a replacement for each of those. So instead of an R squared, you'll see reported a pseudo R squared, which is trying to get at the same idea. How well does our set of X variables fit the outcomes that we actually see? But instead of using the sum of squared residuals as our primary measure of accuracy or fit, we replace that with the value of the log likelihood, the joint probability of observing the outcomes that we see. So the higher that probability is, the better our model is doing. So this so-called pseudo R squared, sometimes referred to as the McFadden R squared, can be calculated as 1 minus the ratio of your model's log likelihood, call that L1, relative to the log likelihood of a model without any x variables. So essentially what this is going to tell us is to what degree does your model outperform a model with no explanatory variables. Right? And it's going to look like an R squared by construction. It's always going to lie between 0 and 1, but it's not going to have that R squared interpretation of the percentage of variation that we can explain. So it's more about to what degree do we outperform that baseline model. So in the case of, let's bring back our Logit model. And what we saw here is a pseudo R squared of 0.34. So it's not saying we've explained 34% of the variation in the data, but our model outperforms the baseline model by 34%, more along those lines. That's not exactly right, but that's a better way to think about it. Okay. Now, as far as, again, measuring how successful our model was, the one thing that we can do in a Logit or Probit model that really doesn't have an equivalent in an OLS model is actually classify our outcomes. In fact, Logit and Probit models are often called classification models, right? So we're trying to take our predictions and say which cubbyhole do we put each observation in? Do we predict that it's a 1 or do we predict that it's a 0? And then we can go back and look what percentage of those observations did we correctly classify. If our model predicted that an individual was going to participate in the labor force and they actually did, that's going to be a correct prediction. If our model predicted that they wouldn't and they actually didn't, that's also correct. Okay. So that's what a classification table does. Just gives us the percentage of correctly predicted outcomes. And the only thing we have to do post-estimation is take that continuous predicted probability and turn it into a classification. So I think it makes a lot of sense. And what the default is have that 50% cutoff, right? So if our model predicts greater than 50% probability of an event occurring, we're going to say we're classifying that as a 1. If that predicted probability falls below 0.5 or 50%, we're going to classify that as a 0. Now, the terminology that comes along with this are the sensitivity and specificity values. But all we're really saying is how well did we predict the 1s and how well did we predict the 0s. So sensitivity is percentage of 1s correctly classified by our model. Specificity, which of the 0s did we correctly classify? What percentage of those observations did we get right? So a perfect model would have the sum sensitivity plus specificity of 200%, right? So think of that as equivalent to a 100% R squared in OLS. Highly unlikely, but the higher those numbers get, the better our model did at, again, classifying those outcomes. So in Stata, we can bring that information up and a lot more that we're not going to focus on right now with the lstat command. So this will give us the sensitivity and specificity for the most recently estimated model. So here, again, only 30 observations, but we've correctly predicted 77% of the 1s. So people that did participate in the labor force, we successfully predicted 77% of them based on their education, age, and marital status. And the people that didn't participate in the labor force, we correctly predicted 75% of those based on those same characteristics. And you get a little breakdown table here showing of all the 30 observations, how many fall into the 4 possible combinations that we predicted a 1 and a 1 actually occurred, or if we predicted a 1 and a 0 occurred, or we predicted a 0 and a 1 occurred, or we predicted a 0 and a 0 occurred. So basically these diagonal elements from upper left to lower right are the correct predictions. Okay, and there's various other combinations of these percentages down here, but generally the two numbers you're going to want to get out of this are right there. It's the sensitivity and the specificity. Okay, one other thing to look at is joint significance testing, both for the purposes of goodness of fit measures and model specification. So because we're not using an R squared or a sum of squared residuals, that F statistic that we enjoy so much in OLS is not on the table. So we use a likelihood ratio test statistic that again does the same thing that the pseudo R squared does. It replaces the sum of squared residuals as a measure of fit with the log likelihood. So again, just scratching the surface here, but it can be shown that if we take two times the difference in log likelihoods between different competing models, a restricted and an unrestricted, that value will follow a chi-square distribution, where the degrees of freedom are the number of restrictions that differentiate those models. So if we go back up here and look at our little Logit model here, what you see is a likelihood ratio statistic where we would normally see an F statistic, right? So this likelihood ratio stat and its accompanying p-value are referencing the null that all of our coefficients in our model are 0. So here we get a chi-square with 3 degrees of freedom because we have 3 variables, equal to 13.89, and a p-value less than 0.01. So we can reject at beyond 1% significance that all of our coefficients are simultaneously 0. Well, we can do the same thing to test a subset of those coefficients. So following this Logit model that had our 3 example regressors, schooling, age, and marital status, if we wanted to test the significance of 2 of those, the command is basically exactly the same as it would be following OLS that would give you an F statistic, but here it's going to give us the likelihood ratio test statistic following a Logit or a Probit. So we can go test A and M. So let's see if age and marital status are jointly significant. And here we get a likelihood ratio chi-square statistic with 2 degrees of freedom, because there are 2 restrictions in the null, equal to 4.73. And if we go to the back of our textbook and look at the associated critical value, we can see that we just barely squeaked by the 10% significance critical value with a p-value of 0.09. So we can reject only at 10% significance or 90% confidence. So again, we've just scratched the surface here looking at Logit Probit models, but that's at least enough to get you started. So I will link to the data source so you can play along with this if you want to, and put any questions you have in the comments, and thank you very much.